I'm really happy and excited to have Peter Bartlett here, and happy to see so many people attending. And yeah, I mean, you can read on the website all kind of his awards, but I want to tell you a bit about more technical stuff. I mean, I met Peter, he claims it the first time in 1992.
91.
91, okay, so it's before most of you were born. And I was very impressed, and I convinced Peter to invite me to visit him in Australia, in Canberra, first for a summer and then for a sabbatical. And Peter was, I mean, he had very kind of insights ahead of the time. I mean, he was one of the first ones to work on neural networks. He published a book in '99 on the theory of neural networks learning, which until today is the most authoritative book on theory of neural networks, and it was way before neural networks were so popular. Peter, in the 90s, he had some kind of groundbreaking work on the complexity of deep neural network, on the VC dimension, which tells you what is the capacity of deep neural networks. Another wonderful work that he did at that time on the bridging between theory and practice was on boosting. At that time, boosting was the major technique in machine learning, and there was some kind of a phenomena that nobody understood, that usually when you talk about the bound on an error, you have the error on the sample plus a term that depends on the complexity of the tool that you are using. And in boosting, you got to zero error on the sample, and you kept boosting and you kept making your predictor more and more complex, and still the results improved, although the theory predicted that they will deteriorate. And Peter had one of the, I mean, I think the first work on explaining this phenomena. Later, he did groundbreaking work on Rademacher complexity that I'm sure that anybody who worked on machine learning knows about it. Even more recently, there is this issue that we have very big neural networks with many, many parameters, and they are being trained on sample sizes that the theory predicts would have to overfit and fail, but they do very well. So we had this groundbreaking work of what they call benign overfitting that tries to explain this counterintuitive to theory people why such big neural networks do so well. So, I mean, it's really a big driving force in the theory of machine learning and in the connection of theory to practice, and I'm really happy to have him here.
Thanks very much, Shai. Thanks for a wonderful introduction, and for inviting me here. It's great to be here. We were just marveling that I've never been to Waterloo before, so fabulous to be here. The talk that I want to present today is about some optimization results motivated by observations with here we go. Motivated by observations of what happens in practice with neural nets. This is joint work with several works with a couple of different groups. So Jingfeng is a postdoc at Berkeley, Yuhang is a PhD student, and then Michael, Song, and Bin are professors at Berkeley. Matus is at NYU, and Kangjie is a postdoc at Columbia. So this is all about some phenomena that have been observed in deep neural nets. These are really at the heart of all of this amazing progress that we've seen recently in AI. I guess for this audience, I don't need to go through. I found a small sample of some of the incredible things that these AI systems can do. Of course, this is really progress in deep learning. All of these successes are built on the foundation of this technology of deep neural networks. From the theory perspective, and of course, we want to be able to build systems that are more effective or even just as effective, but don't make such excessive use of computing and data resources. On the theory side, there's so much that we really don't understand. There are lots of aspects of the behavior of this methodology of deep learning that are really surprising from a theoretical perspective. So normally when we design machine learning methods, we're concerned with three fundamental issues and the trade-offs between them. So there's the issue of what we can represent with the kinds of systems that we work with. Let's say deep neural nets or transformers or whatever. You know, what's the quality of predictions we can get from the best in that class. There's the optimization issue of, you know, we go and get a bunch of data. We need to find, let's say, parameters of our neural net that fit that data well. And there's the generalization issue. You know, given that we can find a prediction rule that does well on our training data, then what happens when we go out and deploy it? Right. So of course, you know, this is very classical. These are the three kind of key issues. In the deep learning setting, you know, the way that these issues seem to be addressed in practice is quite different from what we're used to. So classically, when we think about, you know, this question of building, doing non-parametric statistical prediction, you know, we're used to using these rich kinds of classes that we can be confident will be able to approximate a very wide variety of prediction rules, relationships that we want to model. In the optimization setting, we're used to working with convex optimization problems, finding some nice convex optimization problem, because then we can give guarantees that, you know, after this many steps, we'll have a good fit to our training data. We're used to working with stable algorithms that consistently improve on the optimization objective. In the generalization direction, you know, we're used to having this explicit control of complexity, statistical complexity of the prediction rules that we're working with, keep explicit control of that, and then use tools from like uniform convergence that say, you know, when we have prediction rules in a class that have this complexity controlled in such and such a way, then sample averages are close to expectations. If we perform well on a training set, we're going to go and do well subsequently for independent data drawn from the same distribution. And we're used to, of course, formulating things in this IID way, right? There's a probability distribution that generates the data. And so, you know, what we see in the training set, you know, is this is how we can be confident it'll be representative. At least that's how we model things. In deep learning, a lot of these things kind of, you know, are really very different. It's a very, very different kind of setting in many ways. On the approximation side, you know, depth seems to be important. You know, there are other approaches, other aspects at least that seem to be really important. Attention seems to play a major role in state-of-the-art methods now. And there are these other approaches to kind of finding good features based on sort of self-supervision methods. In the optimization direction, you know, far from having a convex criterion, we have these ugly non-convex optimization problems. It's very difficult to say very much about how to give general guarantees about the performance of those methods. And yet in practice, we can find very good solutions. And it seems to be that the key is over-parameterization, that if you have many parameters, then finding a good solution in practice seems to be much easier. Far from stable algorithms, the practitioners choose large step sizes where we see instability in the behavior of the algorithm. We see the objective, you know, bouncing up and down through training, you know, in a way that's quite different from the kind of classical optimization theory view. And in generalization, you know, far from having explicit complexity control, in fact, you know, in this over-parameterized setting, Shai mentioned this in his introduction, you know, we often find we get good solutions that are kind of too good to be true, you know, very good kind of a global optimum because we could get a perfect fit to training data. And in an over-parameterized setting, there's a big set of such solutions, and it's the optimization algorithm that's controlling which elements of that set we converge to. And that seems to be crucial for the statistical performance of these methods. The complexity is getting controlled by the choices that we make in optimization. So these optimization and generalization aspects really get mixed here. It's not like they're decomposed in the classical way. And far from having uniform convergence, we're finding a perfect fit to noisy data in this setting. So there's this benign overfitting phenomenon that Shai also mentioned, which is really really fascinating, and that's very different from the sorts of settings where these classical tools apply. And of course, we're nothing like an IID setting. I think in a lot of the very powerful models that are being used today, the data that's used for training those models is very different from the way we want to use it. It seems like we're learning features from that data and then going ahead and exploiting those models in all sorts of different directions. So this is really quite distinct from the kind of classical approaches we've had to analyze the statistical aspects of these methods. Okay, so in my talk today, I'm really focused on optimization and on some of the implications for generalization. So I'm going to be talking about the practitioner's choices of large step sizes in optimizing neural nets, and what we can say about that, and in the implications for generalization, how the optimization methods control complexity, in particular for logistic loss, which is kind of the canonical loss that gets used in settings with discrete choices. For instance, in LLMs, where you have a discrete set of tokens that you're choosing, that you're trying to predict. Okay, so that's the kind of more narrow focus of my talk today. I'm going to actually start off with something that's really very simple. It's just logistic regression, classical discrete prediction, and the optimization problem here is convex, right? So there's nothing about the non-convexity that's arising here, but I want to say a little bit about what consequences choosing large step sizes have for the optimization problem. So initially, this is just about optimization, where you choose a step size that's larger than the classical optimization theory would suggest. And then we'll look at what happens in neural nets, again in the setting with logistic loss, so discrete prediction setting. And then we'll look at what implicit bias gradient descent with logistic loss imposes on the solutions. So what's the nature of the solutions that gradient descent approaches? When we're think of this over-parameterized setting where there's a big set of good solutions, and somehow this algorithm is choosing one of those. What are the consequences of the optimization algorithm in the kinds of solutions that we see? Okay, so let's start with logistic regression. So first order gradient methods, just measuring a gradient and taking a downhill step. These are ubiquitous in modern machine learning. We're going to be talking about batch gradient descent. Of course, there are stochastic methods, but these are things that rely just on gradient measurements of an objective. And as I said, there's this tension between optimization theory and practice. So think of the updates. This is just for a batch gradient, full batch gradient descent setting. So W here is our think of it as a parameter vector, and the update from time t to time t+1 is in the direction of the negative gradient of an objective, capital L. So think of that objective as the empirical risk, so the sample average of loss incurred on some data set. When we look at that loss as a function of the parameters WT, right? So the big question here is, well, how do we choose this step size parameter eta, right? The coefficient in the update, moving in this downhill direction. How big a step do we take? So the classical view of this, here's a bit of a cartoon. Step size is on this vertical axis. The classical view is, we think about very small values of step size. We think about that discrete update as just a time discretization of a differential equation. So we'd ideally want a gradient flow that would be moving down this loss landscape, and we're approximating that with discrete steps. So we better make those steps nice and small. This is where most of the theory lies. Of course, if we pick our step size too large, we should expect things to just diverge, blow up, and that would be a terrible choice. Turns out in between, there's this kind of strange behavior where you see some sort of oscillations, some sort of instability, but it's only transient. And actually, as long as the step size is not too large, things do converge. It turns out, at least for neural nets, this is where a lot of the practice lies. It's in this middle range. Practitioners have found that you can do better by picking a large step size where you certainly don't have this monotone decrease in the objective. So that's somewhat surprising and motivates a lot of the results I want to tell you about. Okay, so as I say, the classical optimization theory view is thinking of gradient descent as a time discretization of gradient flow. So here's a differential equation. W as a function of t is our parameter vector that's moving through the parameter space, and the derivative with respect to time of t is in this negative gradient direction. So we're doing this gradient flow downhill in our loss landscape. L is our loss function. So everything here, the parameters lie in RD, and our loss is some bounded below real value function. Okay, and gradient descent, you can think of that as just a discrete time discretization of that gradient flow equation. So it's a difference equation that looks at the gradient that you measure at time t and updates WT discretely. There we go. So this dates back a very long time. Allegedly, Cauchy was the first to propose it. Certainly, he did propose it in the mid-19th century. Here's a picture from Francis Bach's website for some kind of looks like quadratic criterion. The red line here is the differential equation, right? Gradient flow. The blue line is for some choice of step size is gradient descent, and it's monotonically decreasing. And you can see, this view of it as a time discretization seems quite accurate in this case. Of course, the red line, this is a computer simulation, so actually the red line is also gradient descent, just with a very, very small step size, right? It's an even better approximation of the gradient flow, of that differential equation. Okay, so we might ask, well, when are we guaranteed that we get a decrease in the objective, which after all is what we want to do? You could just take a second order Taylor approximation of the loss. So we look at the loss at the previous value of the parameter, and then do a second order Taylor series expansion around that. So we have WT plus 1. So we kind of mix. Okay, so the Taylor series expansion involves the gradient and the second derivative of the loss, and I'm saying it's exact if we pick the second derivative at some point, psi in between WT and WT plus 1. And then when we look at the step that we're taking, which is negative eta grad L at WT, and plug that in for the difference between WT plus 1 and WT, we get this expression, okay, which is promising. We're seeing a minus, a negative quantity with a norm squared of the gradient there in that first order term. Okay, so we just have to worry about what happens with the second order term. The second derivative there is at some psi between the two. Well, we can upper bound that second derivative term in terms of the biggest magnitude that this quadratic form can take. That's just lambda 1 here is the largest eigenvalue of this matrix, right? And psi is somewhere between WT and WT plus 1. So let's take the largest eigenvalue that we see along that line between those two. Okay, so this is very, very straightforward. We immediately get an upper bound on the loss that we'll see at the next step. And if we can ensure that this term that we subtract is a positive quantity, then great, we get a decrease in the loss. Okay, this is really classical. So we want this 1 minus step size over 2 times biggest eigenvalue to be positive, right? And then all is good. That's a sufficient condition for the loss to strictly decrease. This is known as the descent lemma in optimization theory. And of course, that condition is step size no more than 2 over the largest eigenvalue, right? So this largest eigenvalue is telling you how steep the criterion is, and we're looking at maximizing that along the path between WT and WT plus 1, right? So we want to make sure that our step size is small compared to 2 over that biggest eigenvalue, or at least that suffices to ensure the loss decreases. And in the quadratic case, it's an if and only if, right? If we pick eta below that value, we get some nice monotone decrease. Pick it above that value, and things diverge, and it's terrible. This is a bad choice. So the quadratic case, where our update is a linear system, it really is an if and only if. Okay, but things are more complex than that. So for instance, in a 3-layer network, in this case trained on MNIST with logistic loss, this is 2 plots of the objective, the evolution of the objective with gradient descent and a constant step size. The green line shows a small step size, and we get just what we might expect. We get this nice approximation of a differential equation. The red line shows something strikingly different, right? We're seeing the objective bouncing up and down initially, and finally getting into a stable region where it looks a lot like a nice, accurate time discretization of the gradient flow again. But these oscillations at the start suggest that locally, at least, we're not stable. We're certainly not satisfying the conditions of the descent lemma, because we're not seeing a monotone decrease in the objective. So when we choose a larger step size, you see these spikes in the training loss, but actually we see a better value out here. After 1,000 iterations, we've got a much better value of our objective. So there seems to be, a sort of a trade-off going on there. And actually this instability that you see, even in simple cases like this, it seems to be really quite typical in what happens in neural nets with gradient descent. You're seeing oscillations of this sort of rise, across a bunch of different situations. So this paper introduced the term the edge of stability, which they use to refer to having the step size at or around that threshold of 2 over the largest eigenvalue. All right, so we'll use that term a little more precisely as having a non-monotone behavior of the objective. Okay, this will be what we mean by edge of stability. Okay, so let's talk about logistic regression. So, this was the case with a 3-layer neural net, so certainly a non-convex optimization problem. Let's replace the 3-layer net with just a linear function. Question?
Yeah, one question. I mean, you're talking here about what kind of fixed step size.
Fixed step size.
Yeah, no change. And what happens when you change the step size as you go along?
Then all sorts of, I mean, things could certainly be different, right? You could choose, in this case, you might think you could do better with a smaller step size initially, and then so actually everything I'm gonna talk about is for fixed step size gradient descent. You can make adaptive choices of the step size and have a much better behavior. We'll see that with any fixed choice of step size, the rate is always like 1 over t, where t is the number of steps. That's classical, and in all of these settings never changes, and it's the constants that change effectively. We'll see this later. For adaptive choices of the step size, you can get kind of exponential convergence. All sorts of things change. So yeah, we're talking about fixed step size choices, and this is an interesting direction. In practice, for deep neural nets, people have these, particularly for transformer models, people have these step size schedules, right? They start off small, get big, and then get small again, and each of those changes seems to be important. So there's a lot going on with these dynamic choices of step size. But here I'm talking about just fixed steps. Good point. Okay, so let's talk about logistic regression. Very, very classical setting, a convex optimization. So here, instead of a 3-layer neural net, our f hat, our parameterized class of functions is just linear. So for input vector x from RD, the real value prediction is the inner product between x and our parameter vector w. And we're using the sign of f hat to predict the label of the label y, and we're considering logistic loss. So think of that value f hat as giving us a predicted probability that y equals 1, and the prediction is 1 over 1 plus e to the minus f hat. Okay, and the loss we consider is the negative log of that predicted probability. I'm sorry, the negative log of the predicted probability of the actual label yi. All right, so you can think of this as an objective function defined in terms of the f hat, but there's a very natural interpretation of that as the sample average of the log loss for the probability predictions made by that logistic model. And the logistic loss, so as a function of y times f of x, the margin, right, a quantity that we want to be positive to get the right sign, is this function. It's sort of exponential to the right when we're getting the right sign, and asymptotically linear to the left. Okay, so this is what logistic regression is trying to optimize, and we're considering fixed step size gradient descent, where L is exactly this sort of quantity, right? Sample average of a loss that looks like this. Okay, so that's the problem. Very, very classical problem, and of course it's a nice convex optimization, convex in the W. So now, instead of the 3-layer neural net that I showed you earlier, this is with logistic regression with 4 different step sizes. The black line there is a tiny step size. It's the conditions of the descent lemma are satisfied, and we get this monotone decrease. And as we increase the step size through these different colors, red and orange and green, we see we're getting more and more instability at the beginning there. But we're getting better values of the objective after some fixed amount of time. So there seems to be this trade-off here. As we increase the step size, we get more unstable, but we get a better asymptotic value. but the rates, look to be the same in all of those cases, right? The asymptotic rate. Okay. And as I say, we're defining this edge of stability regime to be where the loss is not monotonic, right? So you're in the edge of stability if the loss is until the point at which the loss decreases monotonically from then on. Okay, and then there's some kind of transition region. What we call the stable region is when the loss is decreasing monotonically. And the result here is that we can identify these phases, the edge of stability phase and the stable phase, in a logistic regression setting. The assumptions we make are, okay, the features are bounded. We don't want to have data having a sort of excess influence on the loss. So let's assume a bound. Let's say just all of the xi's are bounded by 1. And we're assuming, and this second one is a strong assumption, we're assuming that there's a direction that gives us the right classification. Right, so there's some unit vector W star so that for all of our training data, we can get the correct sign for each of the yi's.
So it's realizable plus margin.
It's realizable with a positive margin, a margin of gamma, right? In a finite dimension setting with a lot of data, this is a strong assumption. So with this assumption, the result is okay, and I guess that assumption means that when you look in that W star direction, the correct direction, we can go off to infinity in that direction and get the loss going down to 0. So that is the optimum. The optimum is at infinity, right? It's not achieved, but we can get as close as we want to it by heading off in the W star direction and driving our parameters to infinity. Okay, so the result is, first of all, one of the very surprising things is the result holds for any positive step size, no matter how large. Okay, so which is sort of, I think, kind of amazing.
It affects the rate.
It affects everything, yeah. For any positive step size, okay, so we have these two phases. There's the initial edge of stability phase, if the step size is large enough. And there's the stable phase. In fact, what we can say in the edge of stability phase holds throughout, but it's most useful in that phase, and it's that the average over iterations decreases at this 1/t rate. Okay, so we get progress in that average sense through the initial unstable part, even though it's not monotonic. On average, we're doing better, but things are going up and down. And then in the stable phase, once we hit a time where the loss decreases below some value, then the loss decreases monotonically from that point on. So this is what we mean by the stable phase. That's a sufficient condition for us entering the stable phase. Not only that, the loss decreases like 1/e⁻t with some constant that depends on the tails of our loss. And the initial value for the tails, so this is a WS in there, so this is just constant over e⁻t. And, we can say there's a sufficient condition for going from the unstable part to the stable phase to the stable phase. And that is, once we get beyond this many steps, then our loss is decreased to the level it needs to be. And also the constant that appears here is no bigger than 1. All right, so, a lot of information on that slide, but it's really just spelling out there is this unstable phase where some progress is happening, might not be monotonic, and then there's a stable phase where we get monotone progress, and it's always at this 1/e⁻t kind of rate here. So the asymptotic rate is always the same, it's just the constants that change. So, some things to notice here. As I said, any step size leads to convergence, no matter how large. But there's a trade-off. This asymptotic rate is 1/e⁻t. The edge of stability phase might not happen. right? So we might already be in the stable phase if we happen to start off at a point and with the step size for which the sufficient condition of the descent limit is satisfied. But we see these two regimes and the transition between them, and there's a trade-off, right? A larger value of eta gives us a better constant factor out here, but at least this condition that we give for the transition between the two gets weaker as eta gets larger. So we might spend longer in that unstable phase if we pick a big step size. Turns out that if you optimally trade those two off, you can get a better convergence rate. So not a better convergence rate, you can get a better use of an optimization budget. So with a constant step size, if you have a budget of t steps, so you're allowed to take t gradient measurements and set the step size to be order of t with an appropriate choice of the constant. So this is ridiculous, right? Ridiculously large. Then it turns out this gives an optimal trade-off. That unstable part where things are bouncing around lasts for no more than half the time, and in the other half you get the eta in the denominator that tells you your objective is down at a 1/t² value. Question?
All of these results are very specific for logistic loss, right? Because even if it's margin, your loss never gets zero.
That's right. Yeah, so everything I'm talking about here is for logistic loss. Absolutely.
So are you able to say something about like the smoothness, like the Lipschitz smoothness of your function at a certain point? Because if you're taking bigger step size, right, based on the first analysis that you have, like if you have this Lipschitz smoothness, then of course you can take bigger steps. So is it anything saying that as you get closer to the optimum, or is there a nicer region, or?
Yeah, so logistic loss. So let me say a little bit. Actually, can I hold off on that and say a little bit about the proof in like one slide's time? It's all about the shape of logistic loss and how helpful that is.
The margin or the norm of W appear in the map?
Does the
margin?
Yes, the margin does appear, and it's in these hidden in the constants, the big O notation. Yeah, so certainly there's like a 1/gamma² that's appearing in these sorts of quantities. Yeah, so that's right. That's been suppressed in the notation. All right, so we get a 1/t² value of the objective after t steps with a constant step size. You can see rates like this if you use things like Nesterov acceleration, so time discretization of a second order differential equation. You can see faster than 1/t rates if you vary the step size. So there's been a bunch of work of that sort. Not as good as 1/t², but faster than 1/t with a varying step size. But getting this 1/t² with a constant step size is somewhat surprising. And it turns out that initial unstable part is necessary to get the improvement. So if you choose eta, apart from trivial cases. So trivial here means that if you're lucky enough to start off at a point where an infinite step in the gradient downhill direction takes you to the optimum, then fine. If you're not, then having a step size that's small enough to ensure a monotone decrease means you can't do better than 1/t. Right? So it really is from this instability that you're getting the improvement. Okay, so let me say a little bit about addressing this earlier question, say a little bit about the proof and what is it about logistic loss that's allows you to choose a step size that's as large as you want. So things really decompose into these two directions. There's the good direction where you're improving the objective. And there's this subspace orthogonal to that where nothing useful is happening. You always get, and the nice thing about the logistic loss is as it decreases, all the derivatives decrease. And so in particular, the sharpness decreases as you move in that direction. And you're always getting with a positive step size, you're always getting some improvement in that good direction. So you're always having things flatten out. And that's behind this edge of stability, you know, on average, things are behaving well. On the other hand, in the orthogonal subspace, you know, you're unstable in that direction. Things are bouncing around, but they're canceling each other. The steps cancel each other out, right? In some sense. So you have oscillations in the other direction that are of order the step size, but they're always reversing. And so on average, they've got little impact, you know, on the value of the objective. And as you progress, those cancelling oscillations get smaller and smaller because things are getting flatter. The sharpness is decreasing as your objective is going down. So you know, this is the property of the logistic loss that is really helpful for that aspect of analysis. Okay, so that's for the logistic regression, so linear predictions. What about neural nets? So, you know, it's straightforward to extend the analysis to the neural tangent kernel regime. So this is, you know, for the folks that haven't heard of this expression, this is the kind of linearization in parameter space of a class of parameterized functions like neural nets. You know, to stay in that regime, you want to know that linearization is an accurate approximation of the points you reach in function space. And it turns out, you know, if the width of a two-layer network is big enough in terms of the step size, then you're guaranteed, in terms of the step size and the number of steps t that you're going to take, then you're guaranteed that you'll stay in this, you know, good enough approximation, and the linear analysis still holds. Interesting thing here is, you know, for a fixed width, you get out of that NTK, out of that linear regime, you know, really very quickly. It's exponentially small in the step size. So that's sort of the cheating view of neural nets, right? Just do you have a result in the linear case, and so we can think of sufficiently wide neural nets where the linear viewpoint is accurate. You can actually say something much stronger, which is in analysis of neural nets. I say here, so I guess let's say two-layer neural nets of any width, so they don't have to be particularly wide. In the case of neural nets, understanding what happens in the unstable part is much more complicated, and we can only do that with this additional assumption that the data is linearly separable, that we actually have a linear problem again, even though we've got this much richer class of functions, and with some conditions. And I'll state them briefly here, and we'll go into a bit more detail in a moment. And actually, for deep nets, the crucial property here relies on the crucial property here is a homogeneity property, that as you get to big values of the parameters, the behavior for two-layer nets, there's sort of predictable large-scale behavior in terms of growth of the parameters. The same thing is true, but with different growth for deep nets as well, and we can say something there. So there's a homogeneity kind of condition. Turns out that both of these are examples where illustrate where the optimization algorithm is really controlling the kinds of solutions solutions to this optimization problem that we find. So we'll see in the case of neural nets that we're really getting this kind of implicit bias that's arising from the gradient descent algorithm. So I want to say a little bit more about that in the second part of the talk. So this is where these, you know, optimization and generalization are really getting intertwined. And it's the, because we're thinking of a setting with these, let's say neural nets with many parameters, where there's a solution that there are many solutions that give the optimum, this sort of optimal value of the objective, and it's features of the optimization algorithm that control which of the elements of that set that we end up at.
And the boundary between the two parts of the talk, so this is all about deterministic gradient descent. Right?
This is all about gradient descent. So actually, we do have results for stochastic gradient descent. In that case, we can show that the new part is that any step size still works in this setting for the SGD. We don't get acceleration. You don't get faster than the classical rates. At least we can't show that you get any faster than the classical rates, as you can with a batch version. Yeah. Any other questions?
So on the previous experimental results, there are
Sorry, I missed that.
the previous experimental results that you show, the three phases of the convergence were obtained with full batch gradient descent.
That's right. Yeah. Yeah, everything I presented has been full batch. But as I say, we can extend the convergence result to SGD. Okay, so let me take a step back for the second part of the talk and say what's known about the implicit bias of gradient descent in a couple of different settings. The first result here is again for logistic regression and what implicit bias it imposes. So let me review that. So this is a result that's a few years old now by Sudri et al. It says if you're working with logistic regression, the analysis is for gradient flow or small step size gradient descent. Again, linearly separable data. So solution is at infinity. Sort of a complicating thing. When you talk about convergence, you're really talking about convergence of the direction. Solution is at infinity, and the result is that you converge in direction to the solution of a particular optimization problem, right? So in a setting, for instance, where the dimension is much larger than the sample size, there are a bunch of solutions there can be a bunch of solutions that have an optimal value of the logistic loss. The solution that you get is in the direction of the solution of a particular optimization problem, and it's this normalized maximum margin problem. So it's minimized the norm of that parameter vector such that the margin, the worst case margin, so the min over the data of yi times f of xi is at least 1. So I've written it here in general way for a parameterized model. This is for a linear model. F is just linear in the W. And I guess, in the logistic regression case, this number of parameters here is the same as the input dimension D. Why is that normalized margin maximization when it's minimizing the norm of the parameters? Well, so if the function is homogeneous in the parameter vector W, that is, by scaling W, we get the scaling appearing outside. L homogeneous means the power L. So in the linear case, L is just 1, right? As we scale the parameters, the function increases with that quantity. Linear is sort of trivial, but this is also true for ReLUs, right? They're piecewise linear with the kink at the origin. So if you scale things up, scale the parameters up for a ReLU network, you scale the output up where L is kind of the depth, the number of parameter layers that you're scaling.
So one thing did you, when you talk about the optimal solution, you talk with respect to the data or with respect to training data? Is it a generalization statement or just an optimization?
This is not a generalization statement. This is just telling you, yeah, which of those solutions do you favor? Right, and it's the solution to, right, so the min here is over training data, that the L that was up there, right, is the sample average of logistic loss on the training data. Yep. Okay, so, this homogeneity is kind of the crucial property that, that makes things work in the logistic regression setting. That was, yeah, okay. And when things are homogeneous, then, you can pull this factor out and consider, this optimization problem min of the scale of the parameter subject to this constraint is the same as maximizing over the choice of W of this normalized version of the margin problem. So this is why it's called a max margin problem. So it turns out, this homogeneity property is what makes things work in the logistic regression case. There are a bunch of results of the flavor that actually, when you have homogeneous parameterized functions and a loss that's got many of the properties of logistic loss, then there are suggestions that the solution should be in the direction of solutions of this optimization problem. They're actually in the direction of a necessary condition for a solution, Karash-Kuhn-Tucker conditions. And the results are not saying that you achieve that you converge in that direction. They're a bit slightly weaker than that. That if you converge, then it's in that direction. In any case, this is the kind of inductive bias that's been observed for homogeneous functions. When we work with large step sizes, we actually need smoothness. The analysis needs smoothness. The only kind of smooth and homogeneous function is linear. So this is not very interesting. So we have to get away from homogeneity. We have to extend things to nearly homogeneous. And the definition of homogeneity is that you scale things up and that scaling comes outside, right, to some power. So order L homogeneity means you get an alpha to the L when you scale the parameters up by alpha, right? In the case of ReLUs, deep ReLUs, this would be L layers that you're scaling up. You get a sort of factor of alpha to the L that appears. When you think about near homogeneity, that's kind of the wrong quantity to work with. Turns out the right way to view it is in terms of this equivalence statement that when you take gradients with respect to alpha of both sides and evaluated alpha equals 1, you get this sort of expression. And looking at how close the left and right hand sides are is the right way to define near homogeneity. What we do in the L equals 1 case, it's just saying those quantities are close to each other. This is. We also need that things are Lipschitz and as I say, smooth. And with that sort of parameterized model, which is, for instance, linear, sure, but also 2-layer nets with fixed second layer weights, let's say. So it's nearly one homogeneous when this function, this nonlinearity, is ReLU-like, for instance, but smooth. Okay, and there are a bunch of cases of bunch of things that look like that, that people have, that practitioners have investigated.
This is the practitioner network is 2.
So, but with depth 2. That's right. And we need the smoothness and Lipschitz as well as this near homogeneity. And for all of these functions, you can go calculate those various coefficients, apply that. And the result is, as long as the data is separable with this class of, let's say, 2-layer nets, class of these nearly homogeneous parameterized functions, but let's think of that as two-layer nets. So non-linearly separable, we're talking about a case where, you know, you have enough parameters to separate things. Then again, you could say something about the stable phase. So quite generally, something about the stable phase. This is, you know, for any positive step size, once the loss gets down below some value, depends on these various parameters of our parameterized constants for our parameterized class. The loss decreases monotonically at a 1/t rate. And it turns out you can show this normalized margin almost increases. You know, I go into the details of that statement, but the normalized margin is being increased in this stable phase. Turns out with a stronger assumption on the data. Okay, so this is a lot like the sort of inductive bias that we're seeing with homogeneous models. With a stronger assumption on the data, namely that it's linearly separable, you can also say something about the edge of stability phase. So under these conditions, you get something like the sort of statement that we saw earlier in the edge of stability phase, something about the phase transition, and the same sort of conclusions as we saw in the logistic regression case, right? That when we've got these near homogeneous parameterized classes like two-layer neural nets with one layer of adjustable weights, we can get any step size converging, we can get acceleration, this 1/t squared. You know, all of those results apply. When you want to go to deeper nets, then you have to go from one homogeneity to richer homogeneity. So, you know, you have this growth. The crucial property there for that inductive bias is what happens far from, for big values of the weights. For deeper nets, the rate of growth as you scale up the weights grows with kind of the depth of compositions of those parameterized functions. So, you know, we have this sort of calculus of near homogeneity. You know, it's just exactly what I said before. The higher order homogeneity, we look at how close the left and right hand sides are here. Turns out the right thing is not to say that they're within a constant of each other, but that the error term is a lower order term. The right way to do that is to say the difference between those two sides is bounded by some sort of polynomial that has the right degree. It's a polynomial in the scale of the parameters. Okay, so the definition that we want for near homogeneity and actually for Lipschitz and smooth involve polynomials in the size of the parameters, because it's all about what happens as the parameters get large, you know, and how things grow there. So with this definition of near homogeneity for a parameterized class, you have this whole kind of calculus. You could say, you know, if I have a multi-layer neural net with near homogeneous things that I'm composing with each other, then I can tell you about the near homogeneity of the whole thing, the whole composition in terms of those properties of the pieces. So you can kind of build up that sort of property of a neural net. You can do that for compositions, for additions, for tensor products, for linear transform, all kinds of things. And you know, that means all of these sorts of things that you compute, parameterized functions that you compute to build up a deep neural net. You know, you can go through these manipulations to work out the near homogeneity of that parameterized class for almost all the things that you would like. The one that we don't know how to do is attention, because of this. The softmax function, if you think about it, at infinity, it's sort of zero homogeneous, right? It's essentially constant as you go up to infinity, and you know, and that's a problem for the definition. So this is the one gap in the calculus. Anyway, in that case, you can skip over this. The key result here is that, you know, if you have a parameterized class, think deep neural net, then once the loss gets small enough, you have this sort of stable phase result that the normalized margin increases nearly monotonically in the sense we saw before and converges. You can see I'm sweeping the details under the rug with the small font here. The loss decreases at a particular rate. The parameters grow And under suitable conditions on this parameterized class, the direction converges again to these KKT points, necessary conditions for a solution to this optimization problem. It's the same max margin optimization problem, but now we've got a FM here. So the original F is nearly homogeneous. This FM is the kind of homogeneous version of it that you get by scaling the parameters up to infinity and scaling the whole thing down so it stays finite. All right, so this is like making F homogeneous by looking at its behavior at infinity. And that's the optimization problem that that you're solving when you use gradient descent to minimize logistic loss. Okay, so this is the inductive bias that these kinds of near homogeneous parameterized classes that gradient descent imposes on solutions for near homogeneous classes like DPRLNs. Okay, so I think this whole area of what the practitioners are working with, the large sample size that large step size that is too large to give any kind of decent approximation to a differential equation. I think it's we're really only starting to explore, and I think it's a pretty interesting direction, and it seems like in modern machine learning methods, this is where most of practice lies. So I'm kind of excited about that direction. All right, I'll give you some pointers to the papers and stop there.
So in non-convex problems, is there also a sense that these large step size could help escape local minimum? Escape local minimum?
Yeah, so that's one possibility. Like the sort of simulated annealing point. What I thought you were asking was the sort of statistical implications. But yes, I mean, it may be that there's some benefit from having a step size that's too large to converge to a solution where things are too sharp, where the second derivative is too high. So that's certainly true, and if you have if you're lucky enough that your local minima all have that form, you're guaranteed not to converge to them. Step size is too large. The other aspect is, this guarantees that the minima that you converge to have a certain curvature, and that may be enough to give some statistical properties. So there are results of that form as well that they're really just saying a necessary condition for a point that you converge to is this sort of sharpness condition, and what does that imply about smoothness, for instance, smoothness properties of a function that you see, and there have been results of that flavor, calculating the impact on smoothness and impact on and consequences for generalization. So this is another aspect that may well be a benefit of large step size. So we really, this is really isolating the optimization benefits, but yeah, there could be other implications.
Is there any regularization for which you could get similar results when the class?
Is there any regularization?
Yeah, for example, regulated one to non-generalistic class, and then you can get similar results.
Right. So if you think about adding, let's say, an L2 regularizer to logistic loss, even with a very, very tiny coefficient, the second derivative there doesn't go to zero as you go to infinity. In the logistic loss case, we can have an arbitrarily large step size because because things become arbitrarily flat as long as we go far enough in the right direction. If you add the smallest amount of a quadratic function, that no longer becomes true then. And that we really do have this cartoon, the red part of the cartoon. So that was absent in the logistic regression case with logistic loss, because you can actually have a step size as large as you like and still converge. But adding a regularizer and you know, there is a threshold now. So it turns out, you know, you could say something about the regularized logistic regression and you know, the nature of the step sizes that you can use there. And we have some recent results actually in that direction that are kind of establishing the boundary between the showing that you get a better performance by being in this blue region, I guess is the kind of quick summary. Yeah.
Maybe I missed this, but so you showed that as the steps, you can take very large step sizes and decrease the loss more quickly. And you also showed that for very large step sizes, you approach the true W star with your WK in direction. But did you also show that the large step size will approach W star faster? In other words, the combination of the two.
In the so no, and the reason is that we don't have this result, at least, I guess is what you're asking about.
Yeah.
Right. So this, I mean, it's in the fine print here. The rate up to these log factors is still 1 over e to t. So the rate of decrease in the stable phase is still 1 over e to t. So in that sense, you know, that holds promise that we could get this acceleration, that by choosing a large eta, we can get that acceleration. The problem is, for this setting, we don't have a result for the edge of stability phase that tells us, you know, how quickly we'll get out of that unstable setting. In this sort of generality, this is about, you know, parameterized classes that satisfy the sort of conditions we see for deep neural nets. You know, if you go back to the 2-layer case, then we do have that result. So in the 2-layer case, if the data is linearly separable, then you can show this phase transition, and that picking a big step size in that case will get you out to you know, a region where the loss is small enough that you're into the stable phase. You get this 1 over e to t, and for the big suitably large choice of eta, you know, that gives the improvement. So that acceleration property we can prove for a much more limited class of parameterized functions. It's this sort of 2-layer neural nets with 1 layer of adjustable parameters.
Thanks.
If you wanted to use this as an ansatz to pick an adaptive step size, would you think that it tells you that you should always be just before the end of the edge of stability, just after alternating?
Yeah, so this is a very good question, and you know, I'll put up the cartoon again. And in the case, you know, in the results that I've shown you here for logistic loss, where there is a you know, where the solution is at infinity, we don't have any red region, and so you know, I think it's you know, inferring a lot to say anything about the choice of step size that might suggest in practice. But the result that I mentioned, the more recent result that I mentioned about adding in a quadratic regularization term. So it turns out there you can see that setting the step size right at the boundary, you know, very close to the boundary, does give this improvement. And that's, you know, I think is suggestive that you really should be looking for this instability. You know, but again, the right choice balances the unstable part and the stable part, you know, with whatever budget that you have. So it's very much the same conclusion there. Setting the bigger step size, you know, at close to the boundary in some sense, is the right choice. in that setting, which is much more like what you expect, where there is a big enough setting of the step size to when things diverge. I think that's a really interesting question. I mean, it's all about a suggestion in some sense rather than that.
There is an adaptive one, the BB step, which is sometimes bigger and sometimes smaller. That seems to work really well. Is that related all to?
And adaptive choice?
There's an adaptive one called the BB, the Barzilai-Borwein step.
Okay.
I don't know if that fits in at all here, because that's sometimes bigger, sometimes smaller. And it seems to do really well.
So there are a bunch of these. What's the adaptive choice based on there? Is this looking at second?
No,
derivative?
it just uses the first derivative.
Just first derivative.
It sort of apes the fact that if you were doing steepest descent on a quadratic and you looked at the level curves, it's useful to stop early, but then you would go down to the middle very, very quickly, right? So it sort of modifies that idea to general functions.
Okay. Yeah. Going to adaptive step sizes, it's much richer and surely there should be benefits. I think it's a really interesting thing. But I don't know about the BB.
Okay, so thanks Peter again. It's 330 and 1331.